Hey guys! Today we'll be hearing from Robert Dix, who's a grad student here at U of I. His work primarily focuses on things that are called modular forms, which are, roughly speaking, really cool functions that kinda sorta like power series, but that deal with almost every single area of math, from number theory all the way to, if you get close to it, homotopy theory. But I won't give too much away. I'll let the experts say the rest. Without further ado, here's Robert Dix. So let's get some introduction questions going around here. So who are you?
Hi, so I'm Robert Dix. I am a third-year PhD student at the University of Illinois in Urbana-Champaign,
Mhm.
and I do number theory research. I'm a math PhD student.
Where did you get your undergrad?
I got my undergrad, my bachelor's and my master's degree at Emory University in 2018.
And how was that experience?
Well, I think it was very rough in a lot of ways. A
Mhm.
lot of people kind of looked at me in a sort of way like, oh, you're so amazing and you're able to do all this stuff. But a lot of times I was really struggling. It could be really hard, but I think that I learned a whole lot and it was very rewarding because it was a very good warm up for the things that I'm doing now. And I feel like I'm much more on top of things because I went through that kind of rough experience. But it was also good in some ways. I learned a whole lot, met a lot of people,
Mhm.
did a lot of things.
What would you say is the best thing about math you learned during your undergrad?
I don't think I really appreciated until I was really in the thick of it how much tenacity is required. And I want to explain kind of what I mean by that. So a lot of
Uh-huh.
people have this notion about math people that math people are just kind of like these magical geniuses who just kind of think about things and they just kind of come up with an answer just kind of out of the blue. What they don't see is, well, to be a little bit cliched, all the long hours, struggling with the textbook, working on
Mhm.
problems. Most people would think of me like, oh, you're a math guy. So you can just kind of like, I don't know, tilt your head in a like 45 degrees towards the north, and then all of a sudden just kind of get an answer. And I have
Uh-huh.
to say that that is absolutely not true. And that's probably not true for anyone, quite literally.
Yeah. And so have you experienced that sort of stuff when you're doing like research nowadays?
Oh yeah,
Mhm.
there are a lot of roadblocks, but I'm very kind of used to struggling in that way, and I don't get demoralized because I know that this is part of the process. And so in my research, I have these moments where I'm kind of like, wow, I people look up to me and they think I'm like this really special guy, and I'm here reading some paper stuck on a couple of pages for several hours, and I'm just kind of like I'd love for that genius to start kicking in.
uh, what kind of stuff do you research? Like, what's your main area of interest?
Ah, yeah. So I mentioned number theory, and so specifically, I work with special functions that are called modular forms. Many, I guess, topics in number theory are somehow related to things which can be expressed in terms of modular forms. And I'll just kind of give a quick example.
Mhm.
There's the notion of what's called an integer partition, and this is quite literally adding and counting. So you take the number five, okay? And the number of partitions of five is the number of ways you can write five in terms of smaller positive integers. So you
Uh-huh.
have four plus one, and one plus two plus one. I can add, okay,
Uh-huh.
uh, and so on and so forth. So that's and to enumerate all of those, I believe that there are seven partitions of five.
Mm.
And so when I say that, it's not at all clear when I describe what a modular form is later, like that these things are related, but it turns out one of the miracles of number theory is that they are.
Uh-huh.
So yeah, somehow these modular forms capture information about number theoretic objects that we might care about.
Mhm. And so that's like what mainly gets you interested in this. Are there like other things that you're like, oh my God, I love this about modular forms. I want to learn everything I can about it?
Well, I think for me, most of it is the number theory side, but
Uh-huh.
a joke that I like to say about for many people or too many people is that I secretly just kind of want to learn everything. Um, but it's
Uh-huh.
becoming less of a secret as I tell more people, so maybe I should stop saying that. But most of my interest in modular forms revolves around topics in number theory.
Yeah, that sounds really nice. So you're talking about these things called modular forms. What are they?
All right. That is a great question. And we're going to talk about modular forms.
Hmm.
Okay, so what is a modular form? Well, It has to do with, well, they are functions. I mentioned that they are special functions, but I have to tell you something about where the functions lie. So first, I'm just going to describe the upper half of the complex plane. So I'll just say, so these are complex numbers, which have imaginary part greater than 0. And you can visualize for those. I imagine much of the audience is familiar with the complex plane, but I'll just kind of write that you can visualize it quite literally as a plane, where on the x-axis you have the real part, and on the y-axis you have the imaginary part. So if you write z as a plus bi, here you have like 1, 2, 3, and then you have like I, 2i, 3i, blah, 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 so on and so forth. So modular forms are special functions on the upper half of the plane. So the thing that I'm kind of shading in right now is the upper half plane.
Yes.
And in particular, they can actually take any complex value. So I defined them on the upper half plane, but they can actually, in the actual codomain, so to speak, you can have any complex number. They satisfy a few special properties. They are differentiable. So they're differentiable as a complex value function, but if you remember calculus, it's the exact same definition. Like I can just write it as this limit, the limit as h approaches 0, f of z plus h minus f of z over h exists for every z inside of the upper half plane. Okay, so of course I'm kind of skipping over some details. So these are limits in the sense of complex numbers, not necessarily the ordinary sense of limits, but the same definition is here. Yeah, so they're differentiable. And then there are some transformation properties that they have, and I want to say what I mean by that. So they are functions, and I'm just going to write it down first, and I'm going to kind of explain what I mean when I write this. So here the variable I'm using is z. And these a, b, c, and d are going to be something which I will describe once this is written down. Okay, so they satisfy this sort of transformation property, but I need to say something about what a, b, c, and d are. And these are matrices inside of SL2Z, which is just to say that they satisfy AD minus BC is equal to 1. So this is the so-called modular transformation properties that they satisfy. But with modular forms, they always come with a weight. So you don't just say modular form. Often you say modular form of weight 2, modular form of weight 4. And so this K is exactly what the weight is. And the weight is unique. Modular forms of weight K. Okay.
Just to interrupt a bit, what does that Z mean in the SL2Z?
Oh, yeah. This is this C here stands for integers. Good question. So to say SL2Z means that each of A, B, C, and D are going to be integers. And then the third condition, there's this notion of power series, which are quite literally like infinite polynomials. So modular forms have power series expansions, but there's a bit of a twist. These are functions that have a power series expansion that look like this. So, of course, I have a z on the left and I have a q on the right. Like, what's going on there? So this q is actually a function of z, which I'll write down. So it's a power series expansion, but I kind of changed the variable using this kind of q function. So I described what modular forms are, but what I've really described right now is actually modular forms of level 1, which is just to say modular forms on SL2Z. There's also a notion of modular forms that is more general, but this is really the meat of the information. Like, if I were to consider certain subgroups of SL2Z, I can just say, oh, this modular transformation property holds for everything in that subgroup. And then condition 3 is going to get a little bit more, it's going to be a little bit more complicated, but it'll have to do with other kinds of expansions that you can derive from F. And they're going to have certain other properties.
Is there a special name for this kind of power series?
There are a few names. You can call this, let's see, a Fourier expansion. And many times in the literature, you'll also see the term Q expansion, where this Q is exactly the Q that I have here. But yeah, good question.
Nice. And so with this definition of modular forms, in some of your research, there's a distinction between weakly modular forms and just plain old modular forms. What like strengthens a modular form away from weakness?
Oh, yeah, that's interesting. Yeah, so there's this notion, I guess the notion is that of a weakly holomorphic modular form. And so what goes into that is the following. So it has to do with this condition 3. And I said that it gets more, complicated for certain subgroups of SL2Z. So in particular, this is something that really makes sense for well, actually, I want to make sure I don't say anything incorrect. But usually when I'm dealing with weakly holomorphic modular forms, it's not usually on level 1, it's dealing with other subgroups. But I'll actually say a word about what I mean by making the condition a bit more complicated. So I'm going to have another whiteboard. So I talked about modular forms, and I'll just let F just be a modular form, essentially what I wrote down before. And I want to introduce a certain operator. This is going to be the slash operator. Technically, this is the weight k slash operator. And it's notated like this. So I have a function, and the way that it acts is in the following way. I'm going to tell you what gamma is, and also the other thing I'm about to write down, z to the minus k f of gamma of tau. So I need to tell you what gamma is. Gamma is going to be some A, B, C, D. Oh, no, I said tau, but actually, so Z and tau appear a lot. So sometimes I may confuse a Z with a tau. So that's supposed to be a Z, and I've written a Z now. Okay, so gamma is A, B, C, D in SL2Z.
The sort of matrices that we were considering before, right?
Exactly. And this J of gamma Z is the following. It's going to be this CZ plus D. Now, I want to say a word about what it means to be a modular form on certain subgroups of SL2Z. So I'm going to say a word about which subgroups. So
okay.
I'll take gamma inside of SL2Z, and I'm going to stipulate that it's a congruent subgroup. And what does that mean? It means it contains a subgroup that looks like this. So this gamma n is going to be the following thing. I'll take matrices in SL2Z such that you have this condition, mod capital N. And this capital N is going to be a positive integer. And when I write this sort of condition, what I mean is that this is entry-wise. So A is going to be 1 mod n, B is going to be divisible by n, C is going to be divisible by n, and D is going to be 1 mod n. So a congruent subgroup contains some gamma of n for some positive integer n. Okay, so why am I doing all of this? It's going to be a bit clear later on. I want to consider now the following. So it turns out that if I hit F with gamma of k for gamma in SL2Z, there's going to be a Fourier expansion that'll look a little bit more wacky. Okay. So this is going to have an expansion that looks like this. And I'm just going to write QH. It is e to the 2 pi I z over h. This h is some positive integer. We're not going to worry about exactly what it is. But in any case, you have a Fourier expansion like this. Now, what does it mean to be weakly modular? What it means is the following. So F is going to still be holomorphic on the upper half plane, or rather differentiable. I mean differentiable, they're the same thing. But if I were to take every single matrix in SL2Z and look at this Fourier expansion, it may be the case that the expansion looks like this. It could look something like where it can start at a negative integer, let's just say. In the previous whiteboard, I said that this had to start at 0. Here, it doesn't have to start at 0. It can start at a negative integer. And so what it means to be weakly holomorphic is that if I were to range over every single gamma in some congruent subgroup, then this expansion can start at something below 0. So we often speak about weakly holomorphic with respect to a certain congruent subgroup.
And are there any like properties of the modular forms that are sort of strengthened when you go from weakly modular to just regular modular?
Well, in some sense, it kind of, by kind of enlarging the class of modular forms, it kind of means it's a little bit more restrictive in some ways because you're dealing with more general objects. That means you have less information, I guess is one way to put it. So sometimes there's a little bit less you can say. And so when you're dealing with modular forms, you have some specific things that happen. Like modular form is more specific, I guess is what I mean to say. In some sense, with weakly modular forms, weakly holomorphic modular forms, you know, you can say it's more general. So if you prove a theorem about those, then yeah, it's more general. But you have a little bit less to work with. So it's a little bit harder to prove sort of more general theorems. Yeah.
Okay. Yeah. And so we're talking about these Q expansions. So through your work, you also talk about these things called cusp forms. What are they and how would they relate to Q expansions?
Well, cusp forms are a kind of modular form. To say what those are, I'm going to focus on SL2Z, and I'm not going to worry right now about congruent subgroups. There is a related notion for congruent subgroups, but I'll just kind of bring it down to level 1, so to speak. Returning to these, a cusp form is going to satisfy both 1 and 2 with no change at all for SL2Z. But for 3, it's going to be even stronger. So I'm just going to kind of write here. A cusp form will satisfy. So another way of saying this is that cusp forms will have no constant term. So in some sense, they relate to Q expansions because they are in fact modular forms, and they do have Q expansions, and their Q expansions have no constant term when you're on SL2Z. When you're dealing with more general things, you'll have also no constant term in the more general expansions that I wrote on the other whiteboard.
And then what about cusp form is like cuspy in a sense?
Oh, well, this has to do with the following thing. So a related object to modular forms is modular curves, is the notion of a modular curve. And in some sense, I talked about modular forms as functions on the upper half plane, but there is another way in which you can think of modular forms as being functions on modular curves. So what is a cusp? A cusp is something that you can add to a certain kind of modular curve to make it compact. What do I mean by that? So I'm going to make some analogy here. And so I'm going to have a new whiteboard, apparently.
Yes, new whiteboards.
So I talked about the complex plane. And in some sense, this is, you can kind of think about this in a natural way as like some two-dimensional plane, but it's a little bit unwieldy because the complex plane is just this plane that just goes out infinitely many directions. So that's kind of not particularly nice to work with for some things. But if I were to replace this somehow with something that's three-dimensional but is a sphere, you've added another dimension, but somehow it's a little bit simpler because it's just a sphere. You know, you have a finite sort of, you've replaced something with like an infinite area with something with a finite volume. And so since we can kind of wrap our minds around it more easily. So there's a kind of a general sort of notion when you're working with geometry and topology that compact things can be very nice. And oftentimes you want to deal with compact things. There is a notion of a modular curve, which is not compact, but you can add cusps to make it compact. And I actually forgot your original question.
Basically, like, what about a cusp form is cuspy?
Oh, yes, that's right. Okay. So if you were to interpret a cusp form in the way that I talked about, as a kind of function on a modular curve, you can think of it as having a value of 0 at the cusp or vanishing at the cusps.
Okay. And then does this sort of condition make proofs easier for considering modular curves, modular forms, if you just had in general like a non-cusp form on this modular curve?
I feel like for certain things, yes. Which is, I know, a bit of a vague answer, but I'll say yes for certain things.
Cool, yeah. And throughout this whole thing, we're always like thinking like modular form, form. But what you've said is they're always like functions, like it's a function on the Fermat plane. Why are they called forms rather than modular functions?
So this is actually very interesting. So modular functions is already a notion. So there is such a thing as modular functions. And modular functions are actually kinds of modular forms. In some sense, they are the same thing in the sense that modular functions are modular forms. So not all modular forms are modular functions. In terms of why that is the case, that's probably some quirk of history because mathematicians have very weird things that happen with names. But the short answer would be that modular functions are something as well. And so we want to distinguish between modular functions and the more general notion of modular forms.
Nice, thank you. And so when you're working with these modular forms, how do you like interpret them and visualize them in your head?
Well, the short answer would be that I don't. So in some sense, when I think about modular forms, there are geometric ways of making sense of modular forms. The way I think about them is I just think about them as Q expansions. They are, some power series in Q, and they have some coefficients. And much of my research has to do with actually dealing with properties of these coefficients directly.
Nice. With these modular forms, you said that they're, especially with like integer partitions, that modular forms can be applied to study these partitions. Can you give us a hint of like how modular forms are used in this manner?
Sure. For a positive integer, it doesn't have to be positive, but I'll make it positive right now. And P of n counts the number of partitions of n. For this P of n, I can construct the following power series. P of n q to the n. Okay, I started at 0. But let's just say there's such a thing. We often call it the empty partition. There's one partition. Let's not worry about where I'm starting exactly. But in any case, you can consider this power series expansion. And something that I believe Euler proved. I believe that this is correct. Okay. So we have this relation, which I believe Euler proved at some point. This P of n. So because of this kind of product identity, you can actually relate partitions to the Dedekind-Eta function, which I suppose I'll also describe. So the eta function, eta of z, the Dedekind-Eta function actually looks like this. And this q from before is exactly e to the 2 pi I z.
Thank you for the clarification.
Yeah, and I will write that here.
Yes.
Okay, so this is the eta function. So in some sense, up to some like scalar factor, you can think about partitions in terms of the reciprocal of the eta function because of this product identity I've written before. So using properties of the eta function, you can deduce things about these coefficients, would be one way in which the world of modular forms is revealed in this kind of pedestrian world of integer partitions in a way that's unexpected.
And so what about this eta function lets us get to modular forms?
Well, the short answer would be that the eta function is actually a modular form, believe it or not. But I have to clarify that it is a modular form in the sense that it satisfies certain modular transformation properties. It is not a modular form in the way that I've written before, but there is a notion, which I'm going to write this down, of modular forms of half integral weights. So I talked about weights, and I kind of implicitly was assuming that the weights I was dealing with were integers. And it turns out that there is a notion of modular forms where you can have modular forms of weight 3/2 or modular forms of weight 1/2. In fact, the eta function, with suitable definition of what exactly that means, is a modular form of weight 1/2 on SL2Z.
Interesting. And have you ever done any research relating modular forms in the Dedekind-Eta function?
Well, I guess not directly. I've only made use of the relations that have already been discovered, I guess, is what I would say. And so actually, one cool thing about modular forms of half integral weight is that sometimes you can use them to build modular forms of integer weight. So with the eta function, there are these notions of like eta products, which is quite literally as it sounds. Like I could take like eta of z and eta of 2z and like multiply them together and multiply some other stuff and get something that is a genuine integer weight modular form. In that sense, this is a connection that is very classical. And it's, I guess, well known in some ways. And I've made use of that in my research.
So you talked a little bit about modular curves before when we were discussing Cusp forms and stuff. What is a modular curve?
That is a good question. And I'll just kind of write this over here. I can take the upper half plane. And before I do, actually, I'm just going to recall the notion of a fraction. So, like, what is a fraction? Just like philosophically speaking, morally speaking. It is a ratio of two integers. Of course, we have a notion of two fractions being the same. You know, if I have 1/2 and I have 2/4, well, we know that these are the same fraction. Like, what do we mean when we say that they're the same fraction? Well, one way of making sense of this is the following. Let's just say 1 times 4 is 2 times 2. So you cross multiply it, and you get the same thing, okay? And so you somehow take these ratios, these pairs of integers, and you identify them in some way. So this is actually a very basic example of what's called an equivalence relation, where you take two things and you just kind of identify them in some way, and it satisfies certain rules. And we're actually going to do the same thing here. I'm going to take the upper half plane, and I'm going to deal with just the level 1 modular curve. And there's a more general notion for congruent subgroups. We're not going to worry about that.
Yeah.
And I'm going to take SL2Z again. And these consist of, they're going to be matrices in SL2Z, which are going to give us an equivalence relation on this upper half plane. So how does that work? We're going to say two points, so Z and Z prime, inside of the upper half plane are the same, you know, in the same sense of like 1/2 and 2/4. We're going to identify them, which I'll write it in this way. If and only if there exists a gamma in SL2Z such that gamma of Z is equal to Z prime. Now, you might be asking, what is gamma of Z? You know, like gamma's a matrix. Gamma's not a function. This is a shit. So when I write this, I'm actually going to mean the following. You can interpret it as a function on the upper half plane in the following way via this recipe, which you'll remember from the transformation law that I wrote down early on. So this matrix here, I might as well give names to the entries, A, B, C, and D. So this is what I mean when I say gamma of Z. This is a so-called linear fractional transformation. And I say that 2 points are the same if there is one linear fractional transformation with Z coefficients, SO2Z coefficients, you could say, that takes one to the other. And so a modular curve is the set of, I guess, classes, which you can think of as your fractions.
Interesting. And so if you had different sets of these like congruent subgroups, then you would get different sorts of modular curves relating to those congruent subgroups?
Yeah, exactly. Yes, that is exactly correct. For each congruent subgroup, there is a corresponding modular curve.
Interesting. And what kind of information can you get about like the subgroup from the curve or the curve from the subgroup?
So I usually don't think about modular curves, I guess, just in terms of, I guess, the subgroup, even though it is a natural question. I usually think about modular curves in terms of being, well, what's called a moduli space for elliptic curves. So that's usually how I think about it. And I can certainly elaborate on that. I'm going to use a new whiteboard because clearly this is an occasion for a new whiteboard. So modular curves as moduli spaces for elliptic curves. Where do I want to start? So I have to define a few things. So for us, as far as we're concerned, in the universe in which we live, an elliptic curve is exactly this. You take 2 points. They lie in some field, would be the technical term. We're going to take points in some kind of field. It might be C, it might be R, so on and so forth. These are going to be points which satisfy an equation that looks like this. I have to say what A and B are. These aren't going to be necessarily integers. I'm going to say that these are rational numbers. So for us, when I think elliptic curve, it's exactly the set of points satisfying an equation that looks like this, and I will say nothing more. And now, what is a moduli space? Well, I'll give you kind of the idea. It like depends on the context. But I'll give the kind of tagline, which I read from some notes approximately a year ago. They are geometric solutions to geometric classification problems.
Mm-hmm.
So what do I mean by classification problem? Well, usually for some class of geometric objects, I want some, there's usually going to be some notion of saying when these two things, well, when two of them are the same, okay? And one technical term often used for that is that of an isomorphism. You can consider two curves or two really objects of basically any type to be the same if there is some isomorphism from one to the other. For certain kinds of geometric objects, you can actually have a different geometric object. And I might as well write down some stuff. So you have some class of geometric objects. For our case, it's going to be elliptic curves. So I might as well just write at the bottom here, e.g. elliptic curves. And you want to classify them. Well, one thing with this notion of sameness, which I'm calling an isomorphism, you can do the following sort of thing. You can consider instead of doing this directly, you can consider instead the following. You take the, I guess I'll just say, set of isomorphism classes of these objects, and e.g. elliptic curves. So when I say isomorphism classes, I'm just like distilling, like for each I guess elliptic curve, I'm taking the elliptic curve but also considering all the elliptic curves isomorphic to it. So for instance, when we talk about fractions, I usually don't say 2/4 or 3/6, I just say 1/2. Like they're all the same fractions. So yeah, you take the set of isomorphism classes of these objects. And sometimes you can give this a geometric structure, whatever that means in the context. And somehow you can study the geometry of this, set of objects of isomorphism classes, and it can give you information about the objects themselves.
And so we would like literally study broad classes of elliptic curves just by studying modular curves.
Exactly. That is the tagline. That somehow, so these modular curves, there's a way of making sense of them as moduli spaces for elliptic curves. And when you study points on the modular curve, well, points on the modular curve correspond to some isomorphism class of elliptic curves. So if you somehow understand the geometry of the modular curve, it will tell you something about elliptic curves. And that's one reason we care.
And so with these elliptic curves, we now have modular curves are super cool because they tell us information about elliptic curves. What kind of things can elliptic curves be used for?
Oh, well, I guess if I wanted to give an answer that was a little bit like cheating, I would say that elliptic curves can tell you about modular forms. But I will also be a little bit more specific. So I'll just kind of give one reason we might care about elliptic curves kind of in daily life. Believe it or not, math has applications.
Yeah.
It's amazing, right? Okay, what do I want to say about this? I want to say the following. Elliptic curves in nature, so to speak. So elliptic curves. One reason we care about elliptic curves is that they actually give us new methods in cryptography. So I'll just write down cryptography. So I admit that this is not something I know a whole lot about. First of all, what is cryptography and in the related field of cryptology? They are the following. This has to do with code making and code breaking. This is obviously going to be of interest in daily life because it's one way we have secure data transmission is because of people who study cryptography and cryptology. So the short answer, or one short answer, I should say, for the question of why we would consider elliptic curves is that they actually have applications in cryptography and cryptology and allow us to create different kinds of codes and allow for secure data transmission.
Yeah. Is there any big theorems that people might know about that have been solved by using elliptic curves?
It depends on which people, I suppose. But if someone's in a math circle, then surely they will have heard about the following thing. But first, I'll talk about Pythagorean triples. Pythagorean triples are integers, might as well be integers, that satisfy, the relation for the Pythagorean theorem.
Yeah.
And so we have x squared plus y squared is z squared. We all spent time learning about this in high school or middle school, so on and so forth. Well, what happens if I replace this 2 with a 3? So we can replace the 2 with a 3. Does this have solutions? in integers, I should say. Or, why not? Why stop it? Why stop there? Why not do x to the 100 plus y to the 100 is equal to z to the 100? Solutions in integers. Okay, and of course you can perhaps understand where I'm going with this. Like you can just replace 2 with something that's greater than 2, and that there are solutions. So it turns out the answer is no, and this is Fermat's last theorem, which is that answer is no. So and actually, so this terminology of Fermat's last theorem is kind of a misnomer because Fermat claimed to have a proof for which his margins were too small to contain them. But no one knew what this proof was if it existed. Many people believe that it doesn't for the following reason. Because it took 350 plus years to prove.
Yeah, sometime around there.
Yeah. So 300 plus years to prove by Wiles et al. And this was proven by using elliptic curves. And actually proving a relationship between elliptic curves and modular forms. So somehow you have this studying the geometric study of elliptic curves and study of modular forms, and the study of modular forms saying something about really, really down-to-earth simple equations.
Nice. What kind of, if you can expound on it a bit, what kind of relationship did they demonstrate between modular forms and elliptic curves?
Yeah. The kind of relationship, it is the following. So this has to do with the so-called modularity theorem. This modularity theorem, in one of the books that I have, there are 11 different versions of this theorem in that book alone, and there are probably a ton of other different versions. So I'm just going to give the following version, which was actually proven, which will require me to say a bit more about some other things. And this will definitely be an occasion for a new whiteboard. I want to say a word about the modularity theorem. So what does it involve? It involves elliptic curves over Q, which is just to say, like, I gave an equation and the coefficients A and B were rational numbers. So that's what I mean by elliptic curves over Q. I'll just say certain kinds of modular forms. So in a way that I'm going to be a little bit vague and non-technical, the modularity theorem essentially says that for each elliptic curve over Q, you can associate in some natural way a modular form. I want to say a word. It's quite technical, and there's a reason that there are 11 different versions of this. This is a very important sort of theorem in all of number theory. But I'm going to say a word about what that means. So for elliptic curves and for modular forms, there is a bit of a link between them. And how does this go? They each come equipped with what are called Galois representations. Okay, so another way of saying the modularity theorem of the 17 billion different ways is that the Galois representation attached to every elliptic curve over Q can be recognized as the Galois representation attached to a certain kind of modular form. It'll be a modular form of weight 2. We're not going to worry about that. Yeah. So what's a Galois representation? Okay, so it is the following. I'm going to think about Q, and I can extend Q to another field, which I'll call Q bar. Q bar consists of all the complex numbers. I can just say inside of C. It consists of the complex numbers which satisfy some polynomial equation over Q. So, for instance, I, so e.g., I, the square root of -1, or a square root of -1 rather, satisfies x squared plus 1 is equal to 0. So that's an example of a so-called algebraic number, okay? And I want to consider the Galois group of Q bar over Q. I want to say that, you can think of these as symmetries of Q bar. So you can take Q bar and you can look at it a slightly different way. And it's really the same Q bar, but you've just kind of like turned it. It's like if you have a ball, if you turn it some number of degrees, you're just looking at the same ball in a different sort of way. So in some sense, these consist of, I guess, isomorphisms from Q bar to itself, if I wanted to use something I talked about before, but now it's a slightly different context of fields. So it's not the same kind of isomorphism, but it has to do with morally speaking, it's the same sort of notion. So these are, you can think about these as isomorphisms of Q bar with itself, you could say. Okay, so what's a Galois representation? I still have to tell you what that is. Well, it's going to be a certain kind. They're going to be certain kinds of functions into certain kinds of matrix groups. You can literally put almost anything you want here, and you'll get some notion of Galois representation. I'm just going to put F. F is going to be for some field. So F is a field, like the rational numbers. And this GLN consists of, well, matrices with non-zero determinant, for those who know about matrices and determinants. So these are going to be, they're going to be certain kinds of functions from this Galois group to certain matrix groups. They're going to be homomorphisms, which is just to say, I'm not going to be super technical about this. These are so-called structure-preserving functions. So somehow both sides have a sort of algebraic structure. These functions are going to respect that structure in some kind of way. So just to kind of summarize everything I just said, elliptic curves over Q come equipped with some kind of notion of Galois representation. You can construct a Galois representation from some elliptic curve. For modular forms, or certain kinds of modular forms, you can do the exact same thing. Modularity theorem says that these elliptic curve Galois representations are really modular form Galois representations. So that's what Wiles proved. And that's one way to think about the relation between elliptic curves and modular forms. And one way I saw it described is the following, that somehow modular forms have the DNA of elliptic curves written on them. And so in some sense, this relation is very tight, is one way to say that.
Nice. And so with all of this, like the adjective of modularity has been attached to basically almost everything we've been talking about. What makes something modular?
That is a good question. And in some ways, I have answered it, though I haven't mentioned that I've answered it. It has to, essentially, the terminology really comes back to modular curves. So the reason modular curves are modular is precisely because they are moduli spaces for elliptic curves. So it comes back to, so the modular comes from moduli. And modular forms, and this is something I haven't really discussed at all, you can think of, this will warrant a new whiteboard, modular forms as differential forms on modular curves. And the way I think about differential forms, and maybe it's not quite technically correct in every sort of context, I just think about them as things you integrate. For instance, from regular single variable calculus, you often think about integrals of functions that are f of x dx. What is the dx? You guessed it, it's a differential form. So in some sense, it's a very similar notion kind of moving in higher dimensions. But sometimes the integrals get more complicated. Sometimes you're not really integrating per se, but that's the way I think about it.
Yeah. Okay. And so basically everything about modular forms relates to the fact that they just like are moduli spaces for these elliptic curves.
Oh, well,
or historically. Historically speaking.
Oh, well, yeah. Well, these modular curves are moduli spaces for elliptic curves, and modular forms are somehow nice functions on modular curves. And yeah, but it's all connected. But the modular curves are the ones that are literally the moduli space, and modular forms are special functions on modular curves.
We can start talking about your research.